My name is Monica Gallegos Garcia. I am a graduate student at Northwestern University, and I'm going to talk about stable mass transfer channel for forming gravitational wave sources, but I am going to heavily focus on merging binary black hole systems. So for my outline, first I'm going to talk about common envelope, then stable mass transfer, give a very quick lightning overview of the results from population synthesis studies, and a little bit about some EM sources that I'm excited about for trying to resolve some of these uncertainties. So for more than 20 years, it was expected and predicted that common envelope would be the main formation channel for forming merging binary black hole systems. And I think this is the case for two main reasons. First, that many of the progenitors for binary black hole systems were expected to become unstable. So earlier in the week, we've had some really great discussions for how we should decide whether a donor becomes unstable to mass transfer. But a very important piece of this, at least for population synthesis studies, is parameterizing this into the infrastructure for these codes. And the way that this is done is through these critical mass ratios. So in addition to a few approximations that need to be done, a very critical piece in how these are integrated is that the same Q-crit may be applied or is applied for the same stars of a particular evolutionary type. So on the bottom, for example, what this may look like is that all hydrogen-rich stars were at once had one particular Q-crit value, another for helium in sequence stars, and then another for evolved stars. So now there are more unique critical mass ratios in current population synthesis codes, but I think that a lot of binaries were expected to become unstable, and it might have to do with how these critical mass ratios were implemented in binary population synthesis codes. And once these codes were once these donors were expected to become unstable, they went through common envelope, which is a very efficient way of forming binaries that are close enough to merge within the age of the universe. So here I'm just highlighting some key parameters that need to be assumed in order to model common envelope in this way. So we have to decide what the core mass of the star is, which is non-trivial. We're all familiar with the efficiency of common envelope itself. And in these rapid binary population synthesis codes, you don't have information about the interior structure of the stars. So this lambda parameter is used to inform the common envelope phase about the different density profiles that may exist in these donors. But we did know that stable mass transfer can shrink the separation of a binary. So here I just wanted to highlight or review very briefly the isotropic re-emission model for losing angular momentum and highlight its dependence on the mass ratio of a binary. So this example is for mass transfer onto a compact object. All of the mass that is transferred may not be accreted, so we need to account for the mass that is lost and calculate its associated angular momentum. And this angular momentum is thought to be the specific angular momentum of the accretor, which depends on the location of the accretor from the center of mass of the system. So for a binary with a large mass ratio, this distance will be very small, sort of the top example there. So the associated angular momentum will not be as high and can even lead to a widening of the orbit. On the other hand, a binary with a smaller mass ratio, more angular momentum will be associated with this mass loss. And what I want to highlight here is that the parameter space where stable mass transfer can lead to a lot of orbital shrinkage is kind of very close to the mass ratios where we're assuming that it was going to be unstable. So this is a diagram to just provide some intuition. But this paper by Reynolds and collaborators has a really great figure that kind of encompasses what happens when you change some assumptions related to this evolution. So a paper that I think really highlights the potential for stable mass transfer to induce a lot of orbital shrinkage is this paper by Van den Heuvel and collaborators in 2017. So when trying to reproduce the properties of this X-ray binary SS433, they took models and said, we're going to assume that all of these models are stable if they have a particular mass ratio and if the donor is expected to have a radiative envelope. So this figure, the x-axis is the mass of the donor and the y-axis is the orbital period of the binary. The line corresponds to the period where, or the maximum period where the donor will still have a radiative envelope, and the shaded regions correspond to where they found this SSE-like in spiral that will form this compact binary. So what this is showing is that for a wide range of parameter space, stable mass transfer can lead to a lot of orbital shrinkage. But this sort of evolution might not be present in the binary population synthesis codes at the time, because most of these were likely assumed to become unstable. So another important ingredient in the story is revisiting stable mass transfer. So this paper by Pavlovsky and Natasha Ivanova in 2017 really was really highlighted the importance of stable mass transfer for forming binary black holes, merging binary black holes. So in an alternative stability criteria that did not rely on Q-crit, but on some different radii, they found a reduction in common envelope systems. And since common envelope was thought to be the main formation channel for merging binary black holes, this reduction actually helped push the predicted merger rate to within the LIGO constraints at the time. Another great example of revisiting mass transfer stability is the work by Hongwei Ge that was later integrated into population synthesis codes, which showed that these critical mass ratios can lead to more stability than what was previously thought. And one thing that I want to highlight here is that this structure for these critical mass ratios is complex, and a more recent paper shows how further complex it can be. So again, this highlights that maybe in rapid population synthesis codes, these Q-crit values may need to be updated to include all of these details for stability. So now looking into what happens when the binary is expected to become unstable. Another piece of this story is revisiting common envelope evolution itself. So in this series of papers by Jacob Klinke and collaborators really emphasized what we have been saying prior, or what the results have been saying prior, but with detailed single star models in MESA. So one of their papers again highlighted that the occurrence of convective envelopes, which was thought to be an indicator for stability of mass transfer, can't be linked to these specific stellar types as we have been doing. And what the figure here is showing is that if you look at the detailed stellar interiors at the onset of common envelope, and try to model common envelope with very optimistic assumptions, the parameter space where you get a successful ejection can be much smaller than what was previously thought. So the x-axis is the donor mass and the y-axis is the radius of the donor, and you can see that that red strip is a pretty thin range within the stellar radii of the donor. So Pablo's paper from 2021, I think really ties in all of these results and further solidified it with detailed simulations in MESA, which modeled the evolution of a donor in an orbit with a compact object all of the way through stable mass transfer and common envelope. So this was an alternative way of modeling common envelope that tracked how the star evolved when trying to emulate this high mass loss rates that you expect during common envelope. So again, we see similar features to what the previous plots shown. The things I want to highlight here are this blue strip where stable mass transfer is not just leading to significant in spiral that can form these high mass X-ray binaries, but it's leading to enough to form merging binary black holes. Yeah, so the x-axis is the black hole mass and the y-axis is the orbital period. But take note that the scales on the bottom panel and the top panel are different. So this yellow tan region are systems that went through common envelope. But again, that went through common envelope and successfully ejected the envelope. And it is, again, a very thin range in orbital period. And actually, the implementation of this common envelope led to a lot of wide binaries instead of binaries that are close enough to merge within the age of the universe. 2 minutes?
Oh, you have 20 now.
Okay, thank you. Okay.
Yes.
All right.
Yeah, no, you're good.
Okay, so here I'm showing some early results from population synthesis codes that started to show a significant contribution from stable mass transfer. And so one thing that I want to highlight here is that at least at the time, this increased contribution that appeared following these updated prescriptions were intriguing. So it was not entirely clear whether this was a robust feature in binary evolution or an effect of turning one of these knobs that we have. And this is, I think, is further emphasized on the left by a paper by Olejek and collaborators, where they investigated this different mass transfer stability criteria. One of the three models led to a lot of stable mass transfer binaries, and the other two didn't. So in a paper of mine from 2021, we looked at the details of binary evolution, comparing the very standard treatments going back 10 years to detailed models from MESA. So at this time, there were a lot of hints that mass transfer was playing a large role, but I think we still hadn't had a direct comparison like this that tried to explain sort of whether we should be expecting this in populations or not. So here I'm showing the outcome of binary population synthesis code, and the colors correspond to different outcomes. So the yellow are systems that went through common envelope but merged. Blue are those that ended up in wide binaries. And the things I want to highlight here is this boundary between stable and unstable systems, again, a result of these critical mass ratios. And here, all of the merging binary black holes are forming through common envelope. So in this paper, we used the method from Pablo Marchant in 2021, reran the simulations for different donor masses and different metallicities and found similar results. So again, this Q-crit or this distinction between stable and unstable is much more complex, and our binary black hole mergers were forming through stable mass transfer. So we wanted to know how this would propagate to a larger binary population. And what we found was that the number of binary black hole mergers is likely overestimated in standard rapid population synthesis codes. And even at a large population scale, stable mass transfer was still the dominant formation channel. So now I'm going to pivot over to the results from binary population synthesis codes, focusing on the studies that showed a significant contribution from stable mass transfer. And as you can expect, the contribution that we're predicting is very uncertain, and it has a lot to do with these critical mass ratios. So these all are, so they're not exactly one-to-one comparisons, but I think it still holds that we're quite unsure of how big the contribution from stable mass transfer is. And then for the sake of time, I'm going to move on to.
You have time.
Oh, okay. Okay.
You have more than 5 minutes.
Okay, sounds good. Okay, sounds good. So there's been a lot of efforts to try to study this contribution. So looking at the evolution in redshift, like Lique did, this paper by Nessel, and also, again, the paper by Olejek. So now looking at the mass ratio distributions. So again, these are not one-to-one comparisons, but a trend that we are seeing is that stable mass transfer is predicted to have this peak at mass ratio between 0.5 to 0.7. And if we are expecting to have a large contribution from stable mass transfer, maybe we should have seen this already in the distribution of mass ratios that we are observing from LIGO. So this begs the question, what are we missing? If we have a better contribution of stable mass transfer, what physics is left to kind of have better predictions for the masses of these black holes that are expected to come from stable mass transfer. So now moving on to the mass distribution, there's these features in the mass distribution where we have tried to pull astrophysical reasoning for why they should exist. So in this nice paper by Lique, when you split up the contribution from common envelope systems and stable mass transfer, you see this really interesting peak at 10 solar masses, which is similar to the peak that we're seeing here in the LIGO results. But again, this begs the question, if stable mass transfer can reproduce a peak at 10, what does this mean for the common envelope systems at these lower mass black holes? So in a follow-up paper, this peak at 10 solar masses was further investigated by Lique, and it's really interesting way of exploring these predictions by population synthesis codes and trying to tie in some analytic calculations, which I think will be a really important piece to sort of convince ourselves that these results are robust. So another property that we can gain from gravitational waves is the spin of these black holes, but calculating and modeling the spins of black holes is very uncertain and elusive. As I say here, there's two general ways that we model the spins of black holes. So on the left here, we can try to map the spin of the black hole progenitor and translate that to what we expect the spin of the black hole to be. But in order to do this, you need the interior structure of the profile and have a good understanding of the angular momentum transfer within the star, how much the star will be spun up by tides. So being able to calculate this is limited to studies that have interior stellar profiles, but it is also limited by all of the uncertainties that we have in stellar evolution itself. So another way to spin up the black hole is by accretion onto the black hole, but again, a lot of uncertainties exist in how efficient this transfer of mass is. But on the bottom here, there are some promising trends. So if we expect the common envelope scenario to lead to the scenario on the left, so basically post common envelope separations will be very small, and this can lead to a lot of spin up of the donor, which can then be translated to a higher spinning black hole. And it is expected that the spin up through mass transfer which may be more dominant in the stable mass transfer case, is not as efficient as what could be expected for common envelope. So it might be robust to expect that common envelope will just systematically produce higher spinning black holes than stable mass transfer. So I think another robust difference is in the time delay. So the common envelope phase, again, is very efficient at shrinking the orbital separation. So the time between when the stars are born to when the black holes merge is much shorter than stable mass transfer. And this can be seen in my paper from 2021, where the dashed line are the black hole, the population that is dominated by stable mass transfer, and the dashed line or the solid line are those that are dominated by common envelope. And if you change some assumptions in the modeling, these two peaks persist. So this has implications for the redshift evolution of these merging binary black hole systems, which Lieke has done a lot of work on. So the idea is that your stars are born, and if a star is born sort of at the peak of star formation rate, the time that this binary will take to merge through common envelope will be very small. So the rate of merging binary black holes through common envelope might follow the star formation distribution, but for stable mass transfer, there will take a longer time to merge, so there will be much more shifted from this star formation rate. And in this paper by Lieke in 2022, she found that not only does the common envelope scenario lead to smaller delay times, but it is forming systematically lower mass black holes than in the stable mass transfer case. So this is the time delay on the x-axis and the masses of the black holes. And here are little notes to see where these two distributions peak. So this is really interesting because it has promising features in what we may expect in the redshift distribution of merging binary black hole systems. So also from Liike's paper is the redshift evolution of these merging binary black hole systems, but split into or binned by different black hole masses. And these slopes indicate that some black hole masses might be, or binaries of higher mass black holes might have a different rate with redshift than lower mass black holes. So I think another promising avenue for this is looking at correlations between black hole properties. And I'm very interested in this realm of merging binary black hole systems. And I'm currently working with the Poseidon collaboration that Kyle mentioned earlier to try to investigate whether we can find features of different formation channels in correlations like the spin and mass ratio of black holes. So I did want to briefly mention this paper because it also introduces other gravitational wave sources. So this is a really cool paper that use a semi-analytical approach to investigate stable mass transfer systems. And what this is showing is that the stable mass transfer scenario can lead to a wide range of final mass ratios in total masses that, depending on the assumptions that you make, span what we are seeing from gravitational waves. And then this is my final slide. Just wanted to have a few words on electromagnetic sources. So this is very biased because I am very interested in X-ray binaries. So we can learn a lot from the communities that are looking at the details of X-ray binary systems, both observationally and also using GRMHD simulations. To get more information on how this mass is being lost during these non-conservative phases, and also the distributions from the spins that we're getting from these X-ray binaries compared to gravitational waves. That's it. Thank you.
Thanks. Questions, comments, thoughts, ideas?
Thank you for the talk. I was wondering if you think like, trying to form my question clearly. Like if we had like 10,000 mergers and we have like the mass distribution, the primary mass distribution, like really narrowed down, how well do you think this will help us answering some of these questions about the mass transfer common envelope stuff? Or do you think we need to combine more than just like the precision in the posteriors we get from LIGO, for example?
Yeah, I think in the very end, we do want to combine observations from LIGO and other EM sources, because I don't think it's enough to just be able to reproduce some distribution in gravitational waves, but also show that the assumptions that we're using for how these mergers are formed also apply to how high mass X-ray binaries are formed, or how other supernovae are formed, stuff like that. So in the end, I won't be satisfied myself until we have a complete prediction of all binaries in the universe, but that might not happen during my lifetime.
Can I just ask you to go back to the slide where you were showing the spin distribution, please?
This one?
Yeah, thank you. So the way that you are spinning up your black hole is by having, I guess, a Wolf-Rayet close to the black hole and tidal interaction, right?
Correct.
But I mean, my only question on that is that you showed in some previous slides that if you go through MESA, you have way more stellar mergers and lower rates of survival of common envelope events, which are supposedly the ones that you should have in order to form the progenitors of these mergers. So my question is, with a lower common envelope survival rate, do you still have all those high spins?
I guess it has yet to be determined.
Okay.
I think there are, so the plot that I showed where stable mass transfer was completely dominating, that involved a different prescription for common envelope.
Okay.
So I think figuring out what prescription for common envelope is still really important, because I don't think we can completely rule it out, especially if we are seeing spin rates that can't be explained by stable mass transfer.
Okay, thank you.
Yeah.
Very nice talk. So can I have a question about, can you comment or explain how do you deal with the supernova kick and estimate or calculate the black hole mass?
Yeah, so in the work that I have done in 2021, it was a very simple prescription. We just wanted to see kind of in the most optimistic assumptions. So for that, we assumed that it would have complete fallback onto the black hole, so it would have no kicks and complete fallback. In Poseidon, there are different, again, prescriptions that you can apply for. So even though Poseidon is using MESA simulations, which limits sort of the parameters that you can change, the supernova prescriptions are still something that you can change. So in the end, it could be up to you what you choose. Yeah.
Quick question about the black hole definition in MESA. Like, I'm just wondering, like, other than mass, like I could imagine, because like after stable mass transfer, donor star become a white dwarf, and creator star like treated as a point mass from the beginning. So like other than mass, or like if we, because there's also a mass like gap between the neutron star and black hole. So like if we redefine that boundary, like does that quite like affect the result, like your paper like 2021? I was wondering.
I don't think it will too much because the mass ratios I think would still be really high or like very unequal. So I don't think it would change it too much because they probably will be going through common envelope. Yeah.
I have a question. In that same work of yours, I forgot a little bit, but did you follow the systems indeed from like initial mass transfer and then the second mass transfer? So did you do both mass transfers?
Yeah, that's a good question. So for the 2021, I didn't. So we didn't have the full grids yet like we do in Poseidon now.
Yeah.
So I used cosmic from 0 main sequence until the formation of the first black hole, and then asked the question, if we followed them with cosmic, what will happen? If we used our grids of Mesa simulations, what's going to happen?
Yeah, cool.
Yeah.
Yeah, so I was mostly wondering because after all the discussions that we've had now about, well, maybe mass transfer is much more conservative, how you think, well, I think it'll affect the effects of Poseidon. Do you have any opinion on that, or how you might take that into account? Or
Yeah, I think, yeah, I guess one of the limitations of using Mesa simulations, right, is that it is much more time consuming to change these variables, like the efficiency of mass transfer. So we have to make much more difficult decisions on what we're going to choose. So right now, I think, at least for my simulations, I only changed it to like, or limited by Eddington accretion or 10 times Eddington accretion. And changing it further would require more.
I meant also during the, like from star to star mostly.
Oh, okay.
That when, you know, it's critical rotation, but now there's a lot of people here saying like, oh, maybe there's no critical rotation.
The cosmic models were probably basically 100.
It's likely that the cosmic models were 100% efficient because they're thermally limited. And so for the first star to star, at least in the 2021 paper,
You kind of have,
they were basically
effectively a
effectively
100%
100%
efficiency
efficiency because we didn't limit.
That's interesting. Yeah.
Yeah.
Okay, cool. Thanks. Yeah.
All right, yeah, let's think more. Oh, one more? Yeah, one more is fine.
A quick question. So I know that in your 2021 paper, you work with solar metallicity. I'm wondering if since then you've looked into how this, if anything changes for lower metallicity.
Yeah, in the 2021 paper, it was solar and subsolar metallicity. The version 2 of Poseidon, which is what I'm working with now, has 8 different metallicities ranging from 2 times solar to like 1,000 solar. So the upcoming results that I'm working on will have a full range of metallicities.
Okay, we'll be waiting for them then.
Mhm.